And now in this lecture we'll answer on two questions. In the first question we'll find out the area of this rectangle ABCD, and in the second question we'll find out the area of this green shape that is inside square ABCD. So we'll start with the first question. In the drawing we have rectangle ABCD. Inside this rectangle we have this semicircle. In addition, we know that this is called AP, that's equals to 6 units in its length. This is line segment PC, that's equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, those four angles inside the rectangle ABCD are right angles. Okay, this is a right angle. This is also a right angle. This is a right angle. This is also a right angle. In the next step, we define the center of this semicircle. This point is point O. And we will find the radius of this semicircle as x. We'll also define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. And we will define the point of tendency of tangent C with this semicircle. This point is point M. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. This is equals to x units in its length according to our definition. Likewise, OE is also the radius of this semicircle. This is equal to x units in its length. We join points O and M together by a straight line. OM is of course the radius of this semicircle. This is equals to x units, and because of the fact that the radius OM that is equals to x, the radius OM is drawn to point M. That is the point of tendency of tangent DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. By doing this construction, we're going to leave the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that said that the sum of the angles in a quadrilateral is equal to 360 degrees. Therefore this 4 facing angle must be equal to 90 degrees in its size. So inside the small quadrilateral DMOA we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must unite this rectangle if not a square. So we go to this quadrilateral, DMOA is rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMOA, side DA must be equal to the opposite side MO, but MO equals to x, therefore the opposite side DA must be also equal to x units in its length. Likewise, in the big rectangle ABCD, side DA must be equal to the opposite side CB, but DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points E and P together by straight line. By joining points E and P, we call that peripheral angle APE. This is peripheral angle APE. that subtend peripheral angle APE subtends on AE, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in size. So this peripheral angle APE must be equal to 90 degrees in its size according to rule 7. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of this circle, and this is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. Actually, we have already implemented rule 7 in our drawing. As I already mentioned before, this is peripheral angle APE that subtends on AE, that is the diameter of the semicircle, and therefore, according to rule 7, peripheral angle APE must be equal to 90 degrees in its size. So the next step, we define this angle as alpha. So, and we focus on the right triangle APE. On the right triangle APE, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the big right triangle ABC is similar to this small right triangle APE. So why the right big triangle ABC is similar to this right triangle APE? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to the small right triangle APE. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to this angle A, since it belongs to the big right triangle ABC, it will be defined as angle CAB. And angle A equals to itself. So if we relate to angle A, since it belongs to this small right triangle APE, it will be defined as angle PAE. Okay, this equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles, they are both equal to 90 degrees, and therefore they are equal to each other. So actually, this is angle ABC. In the right big triangle ABC, and it is equal to this angle, that is actually angle EPA, in the right small triangle APE. So repeat again, angle ABC in the big right triangle ABC equals to angle EPA in the small right triangle EPA. They are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle ACB. In the right big triangle ABC, and it is equal to this angle, that is actually angle PEA. The right small triangle APE. So if you again, we found out that angle ACB in the big right triangle ABC equals to angle PEA in the small right triangle APE. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually prove that all the triangles of this big right triangle ABC are correspondingly equal to all the triangles of this small right triangle APE. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The big right triangle ABC is similar. This is the sign of similar to the small right triangle APE. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the small right triangle APE over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE over side AC of the big right triangle ABC. So repeat again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. That side AP of the small right triangle AP over side AB of the big right triangle ABC equals to side AE of the small right triangle AP over side AC of the big right triangle ABC. According to what is given as the question, AP equals to 6 over AB. AB is the missing side, so we leave it as it is. And it is equals to AE. AE is the diameter of this semicircle, it is equals to 2x over AC. AC in total equals to 6 plus 5, that is 11. So in total, we found out that 6 over AB equals to 2x over 11. Here we will first multiply this equation. And we get that 6 times 11 is 66, and it is equal to 2x times AB. So here we divide this equation by 2, and we get that 66 over 2 is 33, and it is equals to 2x over 2 is x, so in total this expression equals to x times AB. So if we found out that 33 equals to x times AB, here we'll divide this equation by x, and finally we get that AB equals to 33 over x unit in its length. So actually, this is side AB of rectangle ABCD, and it is equals to 33 over x unit in its length. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is CB. So today we found out that the area of this rectangle ABCD must be equal to AB times CB. AB is 33 over X over CB. CB is X. So today we found out that the area of the rectangle ABCD equals to 33 over X times X. You have X in the numerator and X in the denominator, so X will get cancelled and we left only with 33. So we found out that the area of this rectangle ABCD is equal to 33 square units. Okay, so the area of rectangle ABCD is equal to 33 square units. And that is the answer to the first question. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. Our mission in this second question is to find out the area of this grand shape. So in the drawing we have square ABCD. In addition, we know that this is line segment BP, this is equals to line segment PC, and this is triangle POC. This is equals to 5 square units in each side. Again, our mission is to find out the area of this grand shape. So first of all, we define the length of this line segment BP as A. But we know that BP equals to PC according to what is given us the question, and BP is A, therefore BC must be also equal to A. So in total, BC, side BC of square ABCD equals to A plus A, that is 2A. And we know that all the sides of any square are equal to each other. Therefore, side AD must be also equal to 2A units in its length. Those two angles are defined as vertex angles when we know that vertex angles are equal to each other. So if we define the size of this angle as theta, then the size of this angle must be also equal to theta because they are equal to each other. We know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles and are located between the parallel lines AD and BC. And therefore they are equal to each other according to Rule 15. Rule 15 states that alternating angles between parallel lines are equal to each other. So those two alternating angles that are located between the parallel lines AD and BC are equal to each other according to Rule 15. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to Rule 15. Likewise, those two angles, are also defined as alternating angles and they are located between the same parallel lines AD and BC, and therefore they are equal to each other according to Rule 15. So if we define the size of this vertex angle as beta, then the size of this vertex angle must be also equal to. If we define the size of this alternate angle as beta, then the size of this alternating angle must be also equal to beta according to Rule 15. Okay? So, actually, those two triangles are similar to each other according to angle similarity rule. That is to say, in both triangles we have angle alpha, in both triangles we have angle theta, And in both triangles we have angle beta. Therefore, those two triangles are similar to each other according to angle similarity rule. So I write it down. The big triangle ADO is similar. This is the sign of similar to the right and to the small triangle COP. This small triangle COP. According to angle similarity rule. And from the fact that those two triangles are similar to each other, we can implement here rule 22 that talks about similar triangles. So, what is rule 22? According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. Okay, so in the drawing we have those two triangles, triangle ABC, triangle DEF, that are similar to each other. And according to this rule 22, the ratio between the areas of those two similar triangles, that is to say, the area of triangle ABC over the area of triangle DEF, that is the ratio between the areas of those two triangles, is equal to the square of the ratio of their corresponding sides. So what is the square of the ratio of their corresponding sides? Side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF, and finally, side CB is the corresponding side of side DF. So, side AC is the corresponding side of side DE. So the square of the ratio of those two corresponding sides is AC over DE squared. Okay, it's AC over DE squared. So the ratio between the areas of those two similar triangles, that is actually the area of triangle ABC over the area of triangle EDF, equals to the square of the ratio of their corresponding sides. This is actually AC over DE squared. Likewise, side AB is the corresponding side of side DF. So the square of the ratio of those two corresponding sides is AB over DF squared. AB over DF squared. And finally, side CB is the corresponding side of side CF. So the square of the ratio of those two corresponding sides is CB over EF squared. CB over EF squared. Okay? So the ratio between the areas of those two triangles, that is actually the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides. So we can implement rule 22 in our drawing. Why? Because we already found out that the big triangle ADO is similar to the small triangle COP. And whenever you have two triangles that are similar to each other, you can implement rule 22. According to rule 22, the ratio between the areas of those two similar triangles, what is the ratio between the areas of those two similar triangles? It is actually the area of triangle ADO, the big triangle ADO, over the area of this small triangle COP. And again, the ratio between the areas of the two similar triangles is the area of the big triangle ADO over the area of the small triangle COP. And that ratio is equal to the square of the ratio of their corresponding sides. Side AD of triangle ADO is the corresponding side of side PC of triangle POC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is located in front of angle theta, and likewise side PC is also located in front of the same angle theta. Therefore, side AD is the corresponding side of side PC. And the square of the ratio of those two corresponding sides is of course AD over PC squared. So the ratio between the areas of the two similar triangles, that's actually the area of triangle ADO over the area of triangle COP is equal to the square of the ratio of their corresponding sides. The square of the ratio of their corresponding sides is AD over PC squared. So this equation is the implementation of rule 22 in our drawing. The area of this big triangle ADO is unknown, so we leave it as it is. Over the area of this triangle COP. The area of this small triangle COP, according to what is given in the equation, is equal to 5 square units. So we substitute the area of the small triangle COP by 5. And it is equal to AD over PC squared. AD is 2A. AD is 2A. Over PC. PC is A. AD over PC squared. So we have to square this expression. So we have 2A over A. We have A in the denominator and A in the denominator, so A will get cancelled. And we left only with 2 squared, it is 4. So in total, we should find out that the area of the big triangle ADO over 5 is equal to 4. So here we multiply this equation by 5. And we get that the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. So if we found out that the area of this big triangle ADO is equal to 20 square units. So those two triangles are similar to each other, and therefore the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of the big triangle ADO over side OC of the small triangle POC. So I repeat again, because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of the big triangle ADO over side OC of the small triangle POC. AD is 2A over PC. PC is A, and it is equals to AO over OC. And again, if we found out that 2A over A equals to AO over OC. So we have A in the denominator and A in the denominator, so A will get cancelled, and we left only with 2. So if we found out that 2 equals to AO over OC. So here we will multiply this equation by OC, and we get that 2 times OC is equal to AO. We define the length of side OC as B, and we'll substitute OC into the equation by B, and we get that 2 times B is equal to AO. So AO equals to 2B. So actually we found out that if the length of this side OC is B, then the length of this side OA is 2B. That is to say, OA is twice as long as OC. Again, OA is twice as long as OC. Okay, so in the next step, I present to you a new rule, and we will implement the new rule in our drawing. The new rule is Rule 23. Rule 23 is true in any triangle, so this is triangle ABC that could be any triangle. In this triangle ABC, if you draw the red line segment AEP from the vertex A, it will divide triangle ABC into two smaller triangles. The first small triangle is triangle ABP, and the second small triangle is triangle APC. Rule 23 talks about those two small triangles that were created by drawing line segment AP in triangle ABC from the vertex A. And according to this rule 23, the ratio between the areas of those two small triangles, that is to say, what is the ratio between the areas of those two small triangles? It is the area of this triangle ABP over the area of this triangle APC. The ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. The base of this triangle ABP is BP, and the base of this triangle APC is PC. And the ratio between their corresponding bases is of course BP over PC. So in total, we found out that the ratio between the areas of those two small triangles, it's actually the area of triangle ABP over the area of triangle APC, is equal to the ratio between their corresponding bases, that is BP over PC. So why this equation is true? Because of the fact that what is the area of triangle ABP? The area of this triangle ABP equals to the base of the triangle that is BP times the height that is edge over 2. Again, the area of this triangle ABP is equals to the base BP times the height edge over 2. Likewise, the area of this triangle APC is equal to the base PC times the height edge over 2. Both small triangles have the same height edge. So the area of this small triangle APC is the base PC times the height edge over 2. So those two expressions are the areas of those two small triangles. So the ratio between the areas of those two small triangles is of course the ratio between those two expressions, because those are the areas of those two small triangles. So what is the ratio between those two expressions that are showing the areas of those two small triangles? We have edge in the numerator and edge in the denominator, so edge will get cancelled. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 also will get cancelled. And we left only with BP over CP. That is to say, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. That is BP over CP. Okay, after we cancelled edge and 1/2 in this expression, we got the ratio between their corresponding bases, because it's actually the base BP over the base PC. Okay, so the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases, that is BP over PC. So we can actually implement Rule 23 in our drawing. Why? Because in our drawing we have the right big triangle, triangle ADC, and we have line segment DO that divides the big right triangle ADC into two smaller triangles. the first small triangle is triangle ADO, and the second small triangle is triangle ODC. So all the requirements of Rule 23 are satisfied, and therefore we can implement here Rule 23. According to Rule 23, the ratio between those two, the rest of those two small triangles that were created by drawing line 7DO in triangle ADC, the ratio between the rest of those two small triangles. So what is the ratio between the rest of those two small triangles? It's actually the area of this triangle ADO over the area of this triangle ODC. And again, the ratio between the areas of those two small triangles is equal to the ratio between the area of triangle ADO over the area of this area of triangle ODC. And that ratio is equal to the ratio between their corresponding bases. The base of this triangle ADO is AO, and the base of this triangle OCD is OC. Okay? The ratio between their corresponding bases is of course AO over OC. So actually this expression is the implementation of Rule 23 in our right triangle, triangle ADC. Again, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. Okay? That the bases are AO and OC, therefore it is AO over OC. We already found out that the area of this triangle ADO is 20 square units, so we substitute the area of triangle ADO by 20 over the area of this triangle ODC. The area of this triangle ODC is unknown, so we leave it as it is over the area of triangle ODC. And it is equal to AO over OC. AO is 2B over OC. OC is B. So we have here B in the numerator and B in the denominator, so B will get cancelled and we left only with 2. So if we found out that 20 over the area of triangle ODC is equal to 2. So here we multiply the equation by the area of triangle ODC. And again, we multiply this equation by the area of triangle ODC, and we get that 2 times the area of triangle ODC is equal to 20. So here we divide this equation by 2, and finally we get that the area of the small triangle ODC is equal to 20 over 2, that is 10 square units. So actually found out that the area of this small triangle ODC is equal to 10 square units. It is very easy to see from the drawing that this big right triangle ABC can go into this big right triangle ADC. That is to say, it's very easy to see that those two right triangles can go into each other according to side rule. We know that ABCD is a square, so all of its sides are equal to each other. So why those two right triangles can go into each other? First of all, side AB of the right triangle ABC is equal to side DC of the right big triangle ADC. Why? Because it is a square. In addition, we know that side BC of the right big triangle ABC equals to side AD of the big right triangle ADC for the same reason. And finally, side AC is a common side that belongs to both triangles. So we can find out that AC equals to itself is a common side that belongs to both triangles. So in total, we found out that all the face sides of the big right triangle ABC are correspondingly equal to all the face sides of this right triangle ADC. Therefore, those two right triangles can go into each other according to side rule. So I write it down. If we found out that the right big triangle ABC congruent, this is the sign of congruent, to the right big triangle ADC according to side rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. That is to say, the area of the big right triangle ABC is equal to the area of the big right triangle ADC. Well, because whenever you have two triangles that can go into each other, they must have also the same areas. So the area of the right big triangle ABC is equal to the area of the big right triangle ADC. But it is very easy to see from the drawing that the area of this big right triangle ADC in total equals to 20 plus 10 is 30 square units. So you can write here that the area of the big right triangle ADC is equal to 30 square units. And from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30 square units. We will derive that the area of triangle ABC is also equal to 30 square units. That is from one side, but from the other side, what is the area of this right big triangle ABC? The area of this right big triangle ABC equals to the area of the green shape plus the area of this triangle, that is 5 square units according to what is given us in the question. So if we define the side of the area of this green shape as x, that is to say the area of this green shape is equal to x square units in its size according to our definition, and then in total the area of this big right triangle ABC will be equal to x plus 5 square units. So from the other side, the area of this big right triangle ABC equals to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. X plus 5 equals to 30. Here we subtract 5 from this equation, and finally we get that x is the area of this green shape, that is the area that we are looking for in this question. X equals to 30 minus 5, that is 25 square units. So if we found out that the area of the green shape is equal to x is equal to 25 square units. And that is the answer to the second question. Repeat again. If we found out that the area of this green shape is equal to 25 square units. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in this first question is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD. Inside this rectangle we have this semicircle. In addition, we know that this is called AP, that is equal to 6 units in its length. This is line segment PC, that equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. Because of the fact that ABCD is a rectangle, all those 4 angles inside rectangle ABCD are right angles. In the next step, we define the center of this semicircle. This point is point O. And we define the radius of this semicircle as x. We define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. And finally, we define the point of tendency of tangent DC with this semicircle. This point is point M. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. This is equal to x units in its length, according to our definition. Likewise, OE is also the radius of this semicircle. This is equal to x. We join points O and M together by side line. OM is of course the radius of this semicircle. That is equal to x. The radius OM that is equal to x. The radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. By doing this construction, we can deduce the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th angle. In total, they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4th angle must be equal to 90 degrees in its size. So inside quadrilateral DMOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we learn to this from quadrilateral DMOA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMOA, the opposite sides must be equal to each other. So side DA must be equal to the opposite side MO. But MO is x, therefore the opposite side DA must be also equal to x units in its length. Likewise, in the big rectangle ABCD, the opposite sides must be also equal to each other. That is to say, side DA must be equal to the opposite side CB. But DA equals to x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points A and P together by side line. By joining points A and P, we can deduce peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and we know that any peripheral angle that subtends on the diameter of the semicircle or circle must be equal to 90 degrees in its side. Therefore, this peripheral angle APE must be equal to 90 degrees in its side according to rule 7. We define this angle as alpha and focus on the right small triangle APE. On the right small triangle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle ABC is similar to this small right triangle APE. So why those two triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to the small right triangle APE. Therefore, angle A is a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can prove that all the triangles inside the big right triangle ABC are correspondingly equal to the triangles of the right triangle APE. And therefore those two right triangles are similar to each other according to angle, similar to rule. Okay, the big right triangle ABC is similar to the small right triangle APE according to angle, similar to rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the right triangle AP over side AB of the right big triangle ABC equals to side AE of the small right triangle APE over side AC of the big right triangle ABC. Repeat again. We derive that side AP of the small right triangle AP over side AB of the big right triangle ABC equals to side AE of the small right triangle AP over side AC of the big right triangle ABC. AP is 6 according to what is given as the equation over AB. AB is the missing side, so we leave it as it is. And it is equals to AE. AE is the diameter of this semicircle, that is equals to 2x. Over AC. AC in total equals to 6 plus 5, that is 11. So in total, we shall find out that 6 over AB equals to 2x over 11. Here, of course, multiply this equation and finally found out that 6 times 11 is 66, and it is equals to 2x times AB. So 66 equals to 2x times AB. Here we divided this equation by 2 and finally found out that 66 over 2 is 33. So 33 equals to 2x over 2 is x, so in total this expression equals to x times AB. Here we divided this equation by x and finally found out that AB equals to 33 over x. So this is side AB of rectangle ABCD, and it is equals to 33 over x units. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, you know that the area of any rectangle equals to the length of the rectangle times the width. And therefore the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is BC. Therefore, the area of rectangle ABCD must be equal to the length AB times the width BC. AB is 33 over x, and CB is x. So in total, the area of rectangle ABCD must be equal to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. In total, we shall find out the area of this rectangle ABCD, that is the area that we are looking for. This question is equal to 33 square units. We finish with the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. The second question, our mission is to find out the area of this green shape. So in the drawing we have square ABCD. We also know that line segment BP equals to line segment PC, and this is the small triangle PO sheet is equals to 5 square units in its size according to what is given as the question. Again, our mission is to find out the area of this green shape. So first of all, we define the length of this line segment BP as A, and because of the fact that BP equals to PC and BP equals to A, therefore PC must be also equal to A. So in total, BC equals to A plus A, that is 2A. And we know that all the sides of any square are equal to each other. So if BC is 2A, then the opposite side AD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta because they are equal to each other, according to the rule dimension. In addition, you know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles and are located between the parallels AD and BC, and therefore they are equal to each other according to rule 15. According to rule 15, alternating angles between parallels are equal to each other. So those two angles are equal to each other according to rule 15. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha. Likewise, those two angles are also defined as alternating angles, and they are located between the same parallels AD and BC. And therefore, they must be equal to each other in their sizes according to rule 15. So if the size of this angle is beta, then the size of this angle must be also equal to beta. So in total, if you found out that those two triangles are similar to each other according to angle similarity rule. That is to say, in both triangles we have angle theta, in both triangles we have angle alpha, and in both triangles we have angle beta. Therefore, those two triangles are similar to each other according to angle similarity rule. And whenever you have two triangles that are similar to each other, you can implement rule 22. So I pick quickly on rule 22. According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the moment we have two triangles, those two triangles are similar to each other. That is to say this is triangle ABC that is similar to this triangle ADF. And according to this rule 22, the ratio between the areas of those two triangles. What is the ratio between the areas of those two triangles? Is of course the area of this triangle ABC over the area of this triangle EDF. And that ratio is equal to the square of the ratio of their corresponding sides. What is the square of the ratio of their corresponding sides? In those two triangles, side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF. And finally, side CB is the corresponding side of side EF. So, side AC is the corresponding side of side DE. And the square of the ratio of those two corresponding sides is equal to AC over DE squared. AC over DE squared. So, the ratio between the areas of those two similar triangles, that is actually the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides. This is actually AC over DE squared. Likewise, side AB is the corresponding side of side DF. And the square of the ratio of those two corresponding sides is of course AB over DF squared. And finally, side CB is the corresponding side of side EF. And the square of the ratio of those corresponding sides is of course CB over EF squared. So in total, we found out that according to rule 22, the ratio between the areas of those two similar triangles, that is actually the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides. So we can actually implement rule 22 in our drawing. Why? Because in our drawing, we have already found out that those two triangles are similar to each other. So we can implement here rule 22. According to rule 22, the ratio between the areas of those two similar triangles, what is the ratio between the areas of those two similar triangles? It is actually the area of triangle ADO over the area of triangle COP. Again, the ratio between the areas of those two similar triangles is actually the area of triangle ADO over the area of triangle COP. That ratio is equal to the square of the ratio of their corresponding sides. What is the square of the ratio of those two of their corresponding sides? The square of the ratio of their corresponding sides, we have here side AD of triangle ADO is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is in front of angle theta, likewise in triangle ADO. Likewise, side PC is in front of angle theta in triangle POC. Therefore, side AD is the corresponding side of side PC. And the square of the ratio of those two corresponding sides is of course AD over PC squared. Okay. So in total, we found out that the ratio between the areas of the two similar triangles, that is actually the area of triangle ADO over the area of triangle COP, is equal to the square of the ratio of their corresponding sides. It is actually AD over PC squared. The area of triangle ADO is unknown, so we leave it as it is, over the area of this triangle COP. The area of this triangle COP is 5 according to what is given as the question. So substitute the area of triangle COP by 5, and it is equal to AD over PC squared. AD is 2A, PC is A, so it is 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2 squared. 2 squared is 4. So in total, we found out the big triangle AD over 5 equals to 4. Here we multiply this equation by 5, and finally found out that the area of the big triangle ADO equals to 5 times 4, that is 20 square units. And again, the area of this big triangle ADO is equal to 20 square units. Those two triangles are similar to each other, therefore the following relationship exists between their sides. Side AD of this triangle ADO over side PC of this triangle POC is equal to side AO of this triangle ADO over side OC of this triangle POC. And again, side AD of triangle ADO over side PC of triangle POC is equal to side AO of triangle ADO over side OC of triangle POC. AD is 2A and PC is A. And again, AD is 2A and PC is A. And this is equal to AO over OC. We have A in the numerator and A in the denominator, so A will get cancelled and left only with 2. So in total, we found out that 2 equals to A over OC. We multiply this equation by OC and found out that 2 times OC equals to AO. We define the length of side OC as B, and we substitute OC by B here, and we found out actually that 2B equals to AO. So in total, we actually found out that if we define the length of this side OC is B, then the length of this side AO must be equal to 2B. That is to say, AO is twice as long as OB. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is Rule 23. Rule 23 is true in any triangle. So this is triangle ABC that could be any triangle. In this triangle ABC, if we draw the red line segment AP, it will divide triangle ABC into two small triangles. The first small triangle is triangle ABP, and the second small triangle is triangle ABC. Rule 23 talks about those two small triangles that were created by drawing line segment AP from the vertex A in this triangle ABC. According to this rule, Rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. The base of this triangle ABP is BP, and the base of this triangle APC is PC. And the ratio between their corresponding bases is of course BP over PC. So the ratio between the areas of those two small triangles is of course the area of triangle ABP over the area of triangle ABC. That ratio is equal to the ratio between their corresponding bases. This is actually BP over PC. BP over PC. So actually, how we arrive to this equation, we know that the area of triangle ABP is the base BP times the height edge over 2. The area of this triangle APC is the base PC times the height edge over 2. So those two expressions are the areas of those two small triangles. And the ratio between the areas of, this is of course the ratio between those two expressions. There are the ratio between those the areas of those two triangles, and that ratio, if we can eliminate edge and 1/2, because we have edge in the numerator and edge in the denominator, so edge we can cancel. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 also get cancelled, and we left only with BP over CP. BP is the base of this triangle BP, and PC is the base of this triangle APC. And the ratio between those bases is of course BP over CP. So the ratio between the areas of those two small triangles is equal to the ratio between their bases. Okay? So we can implement Rule 23 in our drawing. Why? Because in our drawing we have the big right triangle ADC. In the big right triangle ADC we have line segment DO that divides the big right triangle ADC into two small triangles. The first small triangle is triangle ADO, and the second small triangle is triangle ODC. So all the requirements of Rule 23 are satisfied, and therefore we can implement Rule 23. Rule 23 talks about those two small triangles that were created by drawing line segment DO in triangle ADC. According to Rule 23, the ratio between the areas of those two small triangles, that is to say, the area of triangle ADO over the area of this triangle DOC. Again, the ratio between the areas of those two small triangles is the area of triangle ADO over the area of triangle ODC is equal to the ratio between their corresponding bases. The base of this triangle ADO is AO, and the base of this triangle DOC is OC. So it is AO over OC. The ratio between their corresponding bases is AO over OC. Again, the ratio between their corresponding bases is AO over OC. So this equation is the implementation of Rule 23 in this right triangle ADC. The area of triangle ADO is 20, so substitute the area of triangle ADO by 20 over the area of this triangle ODC. The area of this triangle ODC is unknown, so we leave it as it is. So we have 20 over the area of triangle ODC equals to AO. AO is 2B and OC is B. Again, AO is 2B and OC is B. We have B in the numerator and B in the denominator, so B will get cancelled, and left only with 2. So in total, if we found out that 20 over the area of triangle ODC equals to 2. We multiplied this equation by the area of triangle ODC, and we found out actually that 2 times the area of triangle ODC equals to 20. Here we divided this equation by 2, and finally found out that the area of triangle ODC equals to 20 over 2, that is 10 square units. Again, the area of this triangle ODC is equal to 10 square units. It is very easy to see from the drawing that this is the big right triangle ABC that convert to this big right triangle ADC according to side rule. Those two triangles can go into each other according to side rule. This is to say side AB is equal in triangle ABC equals to side DC in triangle ADC, where ABCD is a square. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC from the same reason. And finally, side AC is a common side that belongs to both triangles, so we can write down that AC equals to itself is a common side that belongs to both triangles. So in total, if we found out that all the three sides of the big right triangle ABC are correspondingly equal to all the three sides of this big right triangle ADC. Therefore, those two right triangles are similar to each other. Therefore, according to all, therefore those two triangles can go into each other according to side rule. And again, the big right triangle ABC can go into the big right triangle ADC according to side rule. And from the fact that those two right triangles can go into each other, we will derive that they have also the same areas. Any two triangles that can go into each other must have also the same areas. Therefore, the area of triangle ABC must be equal to the area of triangle ADC. But the area of this triangle ADC, in total, it is equal to 20 plus 10, that is 30 square units. So we can write here that the area of triangle ADC equals to 30 square units. And from this equation, the area of triangle ABC equals to the area of triangle ABC equals to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is equal to 30 square units. From one side, but from the other side, what is the area of this right triangle ABC? It is equal to the area of the green shape plus the area of this triangle POC, that is 5 square units according to what is given us in the question. So we define the area of this green shape, that is the area that we are looking for in this question, as x. That is to say, the area of this green shape is equal to x square units according to our definition. Therefore, in total, the area of this triangle ABC must be equal to x plus 5 square units. So from the other side, the area of triangle ABC equals to x plus 5 square units. So from the other side, the area of triangle ABC is equal to x plus 5 square units. From one side, it is equal to 30 square units, and from the other side, is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. Okay, we will derive that x plus 5 equals to 30. Here we subtracted 5 from this equation, and finally found out that x equals to 30 minus 5, that is 25. X is the area of this green shape according to our definition. So in total, if we found out the area of this green shape, that is the area that we are looking for in this question, is equal to 25 square units. Okay, thank you very much.